Hi folks, we're going to take a look at number 19 on page 269. So here we've got a cylindrical container that has to have this particular volume. And they tell us that the cost of the base and the lid, so the top and bottom, is this price per centimeter squared, whereas the side walls is this price per centimeter squared. And they want us to determine the dimensions of the cheapest possible container. So since we're talking about building the container, we're talking about the surface area. All right, so we've got a cylinder. And since we're looking for the dimensions are given by the radius and the height. All right, and what we're trying to do is minimize the cost, but this cost, as I said, is going to be related to the surface area. So the first two things we're going to build are the top and the bottom. So 2 pi r squared gives us the area, and then the cost will just be 0.005 times the area of that total. Okay, so it's going to be 0.005 times 2 pi r squared. So the area of the base and the lid times the cost per centimeter squared for those components. All right, and then it's going to be adding to that the cost of the sidewall, which is 0.0025 dollars per centimeter squared times the area of this sidewall, which of course is given by 2 pi RH. All right, so we can clean this up a little. So this will be 0.01 pi r squared plus, I guess this will be 0.005 pi RH. But we still have the issue of 2 variables in our function. All right, we need to bring that down to 1. But they give us this extra piece of information. They give us the total volume of the can. And of course, the volume is given by pi r squared h. We know that volume is 4,000. And we can now use this to isolate one variable in terms of the other. All right, I want to avoid working with the r squared. If I just had an r squared in the equation, that would be fine, but I also have an r, which would require bringing in a square root, which I don't want to do. Whereas this h here, nice and easy to isolate and won't give me something too difficult when I plug that back into the equation. So h is equal to 4,000 over pi r squared. All right, so let's do the substitution. So 0.01 pi r squared plus 0.005 times pi times r times h, which we are now replacing by 4,000 over pi r squared. And let's just clean this up to get our final model. 0.01 pi r squared plus, I don't want to take any chances, so I will use my trusty calculator. 0.005 times 4,000 is 20. Okay, and of course the pi's reduce. One of those r's reduces in the denominator, so I'm left here with 20 over r. All right, so this is our model for the cost in terms of radius alone. Okay, and our domain here, well, r has to be greater than 0. So since our domain is not a closed interval, I'm going to have to test at the end whether the critical point I get is indeed a minimum. And speaking of that, we're now going to find the derivative in order to find those critical points. All right, so derivative here. So just 0.01 pi is just a constant, so derivative r squared is just 2r. So 2 times 0.01 is 0.02 pi times r. Okay, plus, and I'm going to consider this as 20 times r to the negative 1. So negative 1 times r to the negative 2 times my constant 20 there. Okay, and of course, in order to find the critical points, I'm going to determine where this derivative is equal to 0. So 0.02 pi r, and this is going to be minus 20 over r squared. And so we're left with this rational equation, which I'm going to solve by multiplying both sides by the lowest common denominator, which of course is r squared. So this still remains 0, so 0.02 pi r cubed minus multiplies by r squared. I'm just left with the 20. And so now we have r. So I'm going to do this all in one shot here. Okay, so the first thing I'm going to do is bring the 20 to the other side. Okay, divide by the constant in front, 0.02 pi, and then take the cube root to isolate r. All right, and let's, since we're working with an application problem, let's find an approximation for this. So I've got 20 divided by 0.02 times pi. All right, and we're going to take the cube root of that, so exponent 1/3, and that gives us 6.83. All right, so about 6.83. But of course, as I said, we need to test that this is indeed giving us a minimum value. So I'm going to test my derivative. So remember, r has to be greater than 0, so 6.83. So let's pick 7, and I'll pick 1, and I'll stick it into this version of the derivative. All right, so let's put in 1. So we have 0.02 times pi times 1. All right, and then we're subtracting 20. Oops, I just realized, made a little mistake there. Let's try again. 0.02 times pi, and we're subtracting 20 over 1 squared. So subtract 20, and we get a negative value as we were hoping to get. And now let's do that with 7.02 times pi times 7. All right, and let's subtract 20 divided by 7 squared, okay, 49, and that gives us a positive value. So not surprisingly, as we were hoping, this goes from decreasing to increasing, so this indeed relates to a minimum value. All right, so all we found was the value of the independent variable that gives us a minimum cost. What we have to do is go back to the question and see what they're asking for. And I go back and I see that what they're asking for is the dimensions for the cheapest possible container. All right, so we've actually found one of the dimensions. Okay, we found the radius is going to be approximately 6.83, and the other dimension is going to be the height, which is given by this relationship here. So 4,000 divided by pi times 6.83 squared. So let's see. And by the way, this is going to be in centimeters. So let's calculate that. So what do we have? We have 4,000 divided by pi times 6.83 squared, and that gives us about 27.29. All right, so there's our answer. So just to recap here, so step number 1 was to determine a function for the thing we wanted to minimize, which in this case here was the cost. All right, this function though was given in terms of 2 variables, so we had to do a substitution to write it in terms of 1 variable. So once we have our model with our domain, we can then go ahead, take our derivative, find our critical points, determine what gives us, in this case here, our minimum value, which turned out to be our lone critical point. And then don't forget to always go back to the question and check to see what's being asked for. Okay, that's it for this one.